All right, we just did exam two, and I want to go through three questions uh, to go over one, the questions themselves, but then also looking forward to the final exam, eventually making sure that you're feeling very prepared for the type of questions that will be on the final. So I've got three slides and three questions to go through, and these are ones where there was a more variety of answers, and I got some questions via email on as well. If you have questions about any other part of the exam, or you want to dive in deeper on any of these, reach out to me. We can set up a meeting one-on-one or during one of our regular Zoom meetings, ask the question, and I can go through it then in even more detail than this or any other part of the exam. So this is a very typical question that we'll see again on the final. And let me go through it and just give some strategies and some tips on how to answer this question. So below are two graphs for landing from a jump. Velocity of the center of mass versus time and vertical ground reaction force versus time are the two plots. Time zero represents when the person contacts the ground, and time 0.8 seconds represents when the person is standing still. So I got to give you all that text so you understand the context of the movement and some of the important characteristics of the graph. So now let me walk you through what this paragraph basically says. Anytime you see a figure, I encourage you to stop and look at the figure, see what the title of the figure is, see what the y-axis is, and see what the x-axis is. In this case, the y-axis is velocity in meters per second, and the x-axis is time. And this is the velocity of the center of mass of the person during landing from a jump. Time zero represents the moment the foot hits the ground, and time 0.8 is when the person is standing still. So you've got to envision all the movements that happen from landing from a jump to when the person's standing still. And so the person squats down, the knees go through flexion, and then they stand back up, ultimately to a standing position. The next plot is the y-axis is force on the y-axis, and time, same time axis as the previous plot on the x-axis. And this is the vertical ground reaction force. This is very characteristic ground reaction force for landing from a jump. Time zero is the moment the foot hits the ground. So in this case, it would be the toes striking the ground. And then time 8 is where the person's standing still. And in essence, this represents the person's body weight, where both feet are on the force platform. All right, so the question is, what is happening kinematically to the center of mass at the moment when the ground reaction force is the greatest? So what we need to do is identify where the ground reaction force is greatest, and then try to understand the what's going on kinematically. So where is the force the greatest? It's this point right here. All right, let me do the best I can at emphasizing that point. Like that red. So that is the highest point. And if I just take a vertical line through that highest point, roughly, as best PowerPoint is going to let me, it's not going to let me get to that highest point. I can make that wider, just so we can see this a little bit more. Okay, so we're right around this region here. What I'm trying to do is go right up to the velocity plot as best I can. All right, and that is the highest point on the ground reaction force. And now we're in this region of the velocity plot. Everything's lined up in time. All right, and so now the question really becomes, what is happening kinematically? Whoops, oh, that's a funny way to do that. What is happening kinematically at this point right here? Now we need to look and understand our velocity versus time plot and make sure we're understanding what's going on. So here we have velocity. We have negative velocities here, positive velocities here. These would be vertical velocities. And negative would be downwards, positive would be upwards. Remember, direction of the velocity vector tells us the direction of movement. So any velocity in the negative region means the person's moving downwards. So we're in the negative region right here, so we know we're moving downwards. Now what's happening to the magnitude of velocities? Well, we can see they're going from -2 to -1.5, -1, -0.5. The magnitudes, the 2, 1.5, 1.5, are getting smaller. All right, the magnitudes are getting smaller and movement is in the negative direction. So movement would be downwards. So the magnitudes are getting slower, velocity is getting less and less and less, which means that velocity, we would say velocity is slowing down. So that's going to take us to this answer, slowing down, moving downwards. Remember, when you see this question, what is happening kinematically, I want you to automatically think two things: which way is direction of movement and what's happening to velocity. Now, know that I can also change this question quite easily, and I can say, what is happening at this moment in time? I can't move that dot, it's going to be messed up. What's happening at this moment in time? And what's happening at this moment in time, or this moment in time, what have you. So know that this question is easy to modify in that I'll ask you for a different moment in time, possibly, or what is happening with the ground reaction force, and looking at this velocity plot where the center of mass is slowing down, moving upwards, something like that. Okay, so just make sure that you have a good understanding not only of this question, but how we can expand this question out. All right, next one was this one, which most of you did really well on this one. 81% of you got this one right. Consider the illustration of vertical PVA, position velocity acceleration, and the vertical ground reaction force. In which region would the vertical ground reaction force be greater than body weight and the runner's vertical velocity be slowing down while moving downwards? All right, so now I've got these regions A, B, C, and D. And now I just need to match up where the ground reaction force would be greater than body weight and where vertical velocity is slowing down while moving downwards. So where do we look? We don't even need the position plot nor the acceleration plot. We really just need to look at the velocity plot. So we can do this a couple of different ways. Where's ground reaction force going to be greater than body weight? This dotted line represents body weight. So A is not above body weight, B is, C is, and D is below body weight. So we've already narrowed it down to B or C. Now we can look at the runner's vertical velocity moving downward. We know that the velocity has to be negative. So now we know we need to be in this region here. These are positive velocities. So that's going to rule that out. This will be upward movement. And we also can see the downward movement here and the upward movement. So right away, we're already in the B, in this region. We've already ruled out A. And now B represents the velocities getting less and less and less. The magnitudes are getting less while movement is in the negative direction, or in this case, downward. So the answer would be B. Again, thinking ahead to the final, I could give you the same exact graph, but I could ask you, in which region would velocity be speeding up, moving upwards? Well, we would just look at which region would be speeding up, moving upwards, so the velocity would have to be positive and the magnitude would have to be getting bigger. D is a funny one, right? At this last region here, we are still moving upwards, but velocity is actually slowing down a bit there. So there's a bit of a negative slope for the velocity versus time plot. Right? So again, you might want to just look at this question a little bit more and make sure you understand what is happening kinematically with A, B, C, and D, because this is a type of question I'll use again on the final, but I'll just rewrite this just a bit. And the last one that I want to go through is this one here. Consider the situation where a box is moving with constant velocity. What would be the relationship between forces, the propulsion force, F propulsion, A, and I've got that labeled A down here, and ground reaction force, A anterior posterior, AP, D. All right, so what's the relationship between these two forces? And the key here is when velocity is constant. Okay, whoops. I need that. When is velocity constant? That's the key to this question. Some of the discussions I've had with folks is you may have thought that the question was asking from starting from a zero velocity or starting from some velocity to getting to a constant velocity. And that's not what the question is. The question is to focus in on this constant velocity. Because when velocity is constant, we know acceleration will be, come on, stay lowercase, will be 0 meters per second per second. No change in velocity will tell us that acceleration is 0. And if acceleration is 0, then we also know that the sum of forces will equal ma. And if a is 0, then the sum of forces will have to be 0. So when we're dealing with horizontal velocity as being constant, acceleration will be 0. That means the horizontal velocity, horizontal forces all need to add up to 0. And the only two horizontal velocities are only two horizontal forces are A and D. Therefore, they're acting opposite direction. Therefore, the magnitudes need to be the same so that they add up to 0. Now, they don't always add up to 0. If the object is speeding up or slowing down, then these two forces will have different magnitudes. So this is another way to change this question is consider a situation where the box is speeding up. What's the relationship between these two forces? Well, now we need to end up with some positive acceleration, which means that the propulsion force needs to be greater than the resisting force. And vice versa, if I say the object's slowing down, well, now this resisting force needs to be greater than the propulsion force in order to get some negative acceleration. All right, so again, good to look at the question, make sure that you understand this question, but then think ahead to the final where I would just need to change this phrase here or change the description of the magnitude of the propulsion force relative to the magnitude of the resisting force. Okay, I hope this helps. If you want to go through something in more detail and you do that on one-on-one, we can set up a calendar appointment or come to one of the Zoom meetings and ask me to go through one of the questions in a little bit more detail. All right, thank you.